So today we have Lucas Grosset for the USRA seminar. So probably many people know already Lucas because he made his PhD in Meudon with Daniel Rouen and Yann also. I don't know. I don't remember.
With Damien, and I work a little bit with Yann too, but he was officially Damien and Daniel.
Okay, so in the centers of galaxies group of the high angular resolution pole, and now he's in postdoc since 1 year. Yes, in NASA Ames, working on the SOFIA experiment. So today, Luca will tell us about polarization and high angular resolution, radiative transfer, magnetic field, and AGN. Thank you, Luca.
Thanks a lot for the introduction. So I'm going to talk a little bit about the work I've been doing over the past few years, including a lot of work actually I did in Meudon. So I'm going to focus especially on the good correlation between polarization and high angular resolution, which are working pretty well together. But I'm going to show that a little bit further. And I'm also going to present a little bit of the tools I've used for the for this project. So to just begin this presentation, I'm going to introduce a little bit the AGN field, which I'm sure large fraction of you are pretty familiar with, but I don't know if like everyone is exactly as familiar as the galactic center group, which is aiming at these objects. So to just do things a bit simple, galaxies is considered having an active nucleus if this nucleus is very bright, so typically 10 to the 36 watts. So this is a picture of NGC 1068, which is one of the closest AGN, and you can actually see the nucleus is pretty bright compared to the galactic disk, and it is considered as active if the nucleus is emitting the majority of the total luminosity of the galaxy. So this is a rough limit, but we have like different stage also. And so this luminosity is assumed to be emitted by a very hot accretion disk close to the very center of the AGN, so surrounding a supermassive object, so typically a black hole of mass between 10 to the 7 or 10 to the 9 solar mass. And so here is a rapid sketch of the very innermost region of the AGN. So we have been working a lot over the past 30 years, 40 years even, to understand how these physics work. And well, there's a lot of evolution on the modeling, but I'm going to discuss that a little bit further. But what I want to focus on here is we are looking at very, rather small regions, so typically between few parsec to maximum 100 parsec, and distance which are pretty large, so typically, the typical like close AGN are between 10 and 20 megaparsec. And also very close to a very bright source. So we need for that very high contrast imaging and high angular resolution to be able to see and study this very not so bright region, very close to this innermost region, and understand further how AGN are actually working. So for just a rapid overview of AGN, we have a bunch of different categories for AGN, but fundamentally this would just be the same type of object, which have like different active phase which are more or less active. But the main difference would arise actually from the viewing angle we have on this object. So this is a model of, so at the very center you can see you would have a supermassive black hole with a accretion disk which is emitting most of the luminosity between basically the ultraviolet and the near infrared. Then you would have in red and brown the optically thick material which is blocking the light from the very center depending on the viewing angle. So if you're in the plane of the equatorial material, you will not be able to directly see the center. And if you see that from the pole, you could actually see that. You have also like this green ionization region, and you can also have some jets which are here in yellow. So the part which I'm more interested in is actually like the brown part, which is opticalistic material, which is not very hot and not very luminous, but we can try to detect that in the near infrared and in the far infrared. But we need for that very high contrast imaging to understand a bit more this region. And as you can see here, the model has been evolving quite a lot. So this is, so after the first model stated by Antonucci about 40 years ago, we have been moving on. So this is one of the first models. You can see like the obscuring material is basically just represented as a well, solid donut with just small features and very simple assumption. And then we have moved very recently to way more complex systems and regions with a lot of moving material, a lot of well, first it's not going to be any solid block anymore. It's going to, we are thinking of more a clumpy region with a lot of different density depending on the location exactly. And so we still have a lot of well, investigation to do to really like constrain and understand this quite complex region in the end. So yeah, just this talk is going to be oriented between like, well, actually 3 parts. I just stated 2 here. So the part which I've been working on the dust in the near-infrared and specifically on the obscuring material and the torus region, which I've been mostly doing at LESI actually. And the more recent work I've been doing in SOFIA on the magnetic field, so more in the mid and far infrared range at slightly larger scale, but still on the same very close object to have the higher angular resolution possible. And also, I'm also going to talk a little bit about the polarization itself to make it understand, because that's actually the basis of my work. And I'm going to discuss a little bit in the end of the radiative transfer code I've been using for the interpretation of the results too. So first of all, a short reminder about polarization. So you can actually have a lot of different mechanisms that can produce polarization from astrophysical sources. And in the, well, in wide infrared range, so from basically visible to far infrared, you can have, well, basically 3 main mechanisms, which is dichroic absorption or emission. So that would actually require not spherical grains, so elongated grains, which are going to have a preferential direction of both absorption and emission. So depending on the wavelengths, if you're looking at regions that are going to emit light, so for example, in the mid and far infrared, you're going to have a specific orientation of the polarization. And if you look now in absorption at shorter wavelengths, you're going to have a flip of 90 degrees of the viewed polarization, because the preferential direction is going to be absorbed and not emitted actually. And then you have scattering, which can occur, well, I stated that with a spherical grain, but it can actually happen with pretty much any shape of grain. And that can actually be efficient at pretty much any wavelength, but I'm going to discuss that a little bit later too. There's some preferential wavelength where it's a bit more efficient for scattering than others. So, well, that's good. We have like this different mechanism, but now the most difficult part in polarization is interpreting and disentangling between this mechanism, because it can actually, well, maybe not all 3, but at least 2 of them be happening at the same time. So I'm going also to present polarization maps. So usually they are just set to represent with the small vectors the main oscillation direction, so the electric field. But when I'm going to present the data in the far infrared, we usually well, represent the magnetic field vector and not the electric field. So that's a 90 degrees rotation, because it's just like easier to represent. But I'm going to well, explain that a little bit further at this stage. But if not specified, all the polarization vector are going to represent the electric field in the presentation. And usually the length is proportional to the degree of polarization. That's what I'm going to do. So for example, in this image, which is a simulation, the degree of polarization is actually higher on the outer bounds of the clump than on the very inner part. So finally, when you, well, so this is a picture of NGC 1068. So we have been observing with Daniel and Damien, well, quite a long time ago now. It's like 5, 6 years in the past. So you can see here that's classical imaging observation of NGC 1068, so at 2.3 microns. And you can, well, and depending on the luminosity of your screen, you might or might not be able to see these small arcs on the well, bottom right part of the image. But if you turn on the polarization, you can actually like really see these structures appearing. So here we can. So this is an image we observed with Damien and Daniel with Sphere 6 years ago, and you're probably already familiar with that. And you can see, like in polarization, all the region where this mechanism I've been talking about before are actually happening. So this is mostly a single scattering, so just scattering on those grain which are on the region we can actually see here. But I'm going to also discuss a little bit more that. But the polarization can actually reveal way efficiently all the structure we cannot directly get access to because of contrast issue, for example. We can see way more detail on the right polarization map than on the intensity map. So now, why did we use Sphere to observe this AGN? So a Sphere, as you may know, because I know a major part of the team is also working on well, I don't know if you're working on Sphere or on Sphere upgrade or on other instrument now, but I know like the Sphere instrument have been developed in large part by the MontAGN team. And so I'm more interested by the high contrast imaging and the very extreme adaptive optics designed for exoplanet and disk studies. And well, of course, it has a high angular resolution with polarization, and so it had been shown that it's really efficient to observe disk around young stars. And so the problematic with well, optically thick material surrounding the center of AGN is pretty much the same. The angular size on the sky is not that different, and the contrast ratio is pretty similar. So it's actually been shown that it's pretty efficient to observe AGNs too, which is very good for us. So here, that's a polarization map of 1068. I'm going to go a bit fast on that because we have been discussing that for a long time now, and you're pretty familiar with it, I guess. So on the left part, that's the polarization degree. And on the right part, it's a specific display of the polarization angle. So to start, just on the left side, you can actually see pretty efficiently like that there's a double cone of ionization. So this is what is giving this hourglass shape of the signal we were detecting. While in the very center, it's a little bit, we have a spot of high polarization of about 10%. You can see that actually like the entire central region is pretty, is very little polarized. So we are like way below 1% of polarization. But in the polarization angle, you can see on the right hand side, you can actually see there are signal in this region. So the angle is pretty well defined, but just the polarization degree is pretty low. So on the right side, so what we have actually been working on the display is to make the scattering a bit more obvious. So this is basically, if you're familiar with the QFI display of young stellar object and polarization in stellar environment, it's pretty much the same idea. So this is a rotating map with the polarization angle. So everything which is black and zero is basically something with vectors rotating around the center. So that is a good sign of scattering happening, because the orientation of the vector when we have a scattering event is going to depend on the geometry of the scattering event, and so the vector are going to be rotating around the central source. So everything which is in black here is like almost certainly scattering happening, and so everything which is not in black, so especially the very central part, which I'm going to be interested in now, are definitely not just scattering, and so we need to investigate that a little bit further. So just to show the contour of the ionization cone a bit more efficiently. So you can see on the right, bottom right and the upper left, you have like these two regions with a lot of different clumps of polarization activity. And on the other equatorial plane, well, we can barely see anything, and you can actually see this region is pretty empty in terms of polarization signal, and the polarization is actually pretty low, even in the well, intermediate region, which is well, I'm going to discuss that later on, but a sign of something blocking the light in this plane, so it cannot interact with matter. I mean, you cannot have scattering in these outer regions, because just light doesn't reach this region because of the blocking of the material in the center. So now I'm going, so this is basically another display of the polarization angle. So the map I shown before is on the right side, and if you just display the polarization angle directly, you have this rotating pattern with like the color changing depending on the azimuthal angle surrounding the center. So it's a bit more easy to see this rotating pattern. So you have the color changing depending on the location around the center. And if you look at the very center, like you have this entire region, which is of pretty constant color, which means that the polarization angle is pretty constant at this location, which is not really expected, because that means it's not just single scattering, and we have to study a bit more the polarization mechanism in this region to understand this center region. So this is a region about like 60 parsec wide on I think that's 30 parsec thick. So yeah, so that's about it for polarization angle. And so when we were working with Damien Daniel to understand this this signal at the very center, we reach well, a similar study and similar problematic on young stellar object with some observation of polarization vectors diverging from the expected pattern, especially on the central pattern of well-defined scattering surrounding the central bright source. So this was done first by Bastien Ménard in 1990 on young stellar object, and then it was on the left side, that's a simulation by Murakawa in 2010 of polarization in young stellar objects. And so you can see actually in the very center, you have a way different polarization orientation, and associated with a low polarization degree, which is actually due to multiple scattering and not only single scattering. So you have a picture on the right side to explain a bit better that. So well, most of the light we are watching is actually just emitted by the very center of the AGN. But because the torus or well, any blocking structure we have in the equatorial plane is too optically thick, you cannot see directly any photons coming from that. But you would be able to see photons which are first emitted, then scattered the first time in the ionization cone. So whether it's a bit up or down in any of the two ionization cone, with pretty low optical depth, so you can actually interact pretty far from the center. And then this scattering could actually redirect the photons in pretty much any direction. And so some of a fraction of this flux would be redirected to the equatorial plane. And if these photons reach the outer part of the torus, it is so that this outer region is of less density than the very center. So it would be actually easier to get a second scattering event in this region, and then scattering toward the observer without traveling through a very high density region, which would most likely absorb the photons. So this was the basic idea, but then it's pretty unlikely to have these two events with exactly the good geometry. So even though we have a large flux at the beginning, we still need to investigate if it's actually possible to get a decent flux of such photons at the end after the double scattering events. So that would actually produce the expected polarization pattern. So for this reason, we have been looking for radiative transfer code that were able to allow polarization observation. So now I've been working on that pretty lately, and there's a bunch of code which are now available. But it was not really the case when I first started my PhD. So that maybe a bit unfortunate. Maybe I just like started 5 years too early for having access to the code. But nevertheless, it's still pretty much for all the code still work in progress to include polarization on this radiative transfer model. So there's a lot of radiative model which are available, but the polarization is often well offered just as a test feature or not well tested in this code. So well the idea we have had with Daniel a few years ago was just to develop our own code based on some work which were already been done in Asia a few years ago. And especially the idea was also to make that working well with AGN, because most of the radiative transfer code were actually optimized for stellar environment. So we were also looking for a bit more versatile code to be able to adapt things a little bit more. And so this is an example of the geometry we were using at the beginning. So with a pretty thick equatorial plane with a high density in the center and a bit smaller one on the outer part, and an ionization cone, which would be able to redirect the photons in the polar direction up to in the direction of the equatorial plane. So I'm going to present the code a little bit later, but the simulation were pretty much able to reproduce the pattern. So you can see the simulation on the right side and the observation on the left side, except that I was not able to simulate the entire environment, which is a bit too, well, I would have way too much, a need for way too much simulation power to be able to simulate the entire region, or we would have a resolution issue with not large enough pixel to be able to compare it with the simulation. But that shows that we were able to detect some photons coming from the central region. We were not well oriented with a single scattering, which is in black in both the model and the simulation here, but were pretty much all well, I would say horizontal, but it's just horizontal of the model, but basically a well-defined orientation of the polarization with pretty low polarization degree, with this feature of double scattering. And if I'm not mistaken, I have the maps of the optical depth and the number of scattering. So everything you see in blue is that's from the simulation. And because we pretty much have the control of everything during the simulation, we can just track where and how many interaction did the photons undergo when we detect them. So everything which is in blue is all the regions where we are mostly getting photons with only one scattering, since they've been emitted by the center. And in green, it's two scatterings. So we can see, like, if we increase the optical depth of the obscuring material in the equatorial plane, it switched from basically you have only like single scattering and not so much material which is blocking enough to have like more complex interaction, up to a well-defined two region where you have the ionization cone with just single scattering photons and the equatorial plane with mostly two scattering photons. And if you increase more and more the optical depth, it's not changing that much the central region, because the photons we are detecting are just basically avoiding this very dense region. So well, if we are above the threshold that just removes the photons coming from the very center to reach the outer part, increasing the density will not change much. And so I've been also doing same investigation on, for example, the cone, ionization cone, and you can see like there's a huge difference here. If you increase the optical depth of the ionization cone up to, for example, like 10 on the left on the last picture, you can see like we have like about 5 scattering events in the entire region, because well, photons are not able to have any material they can actually get to interact and exit the medium rapidly, because both the torus and the ionization cone in that case are way too optically thick. So due to that, we are able to constrain, to have first like rough constraint on the optical depths required for both the ionization cone and the torus, which was pretty compatible with the expectation, but a bit higher. So I don't know if you know, I've not stated that here, but it's around 150 to 200 in optical depth in the visible, which is a bit higher than what we were expecting. But now I've been working also with new data from SOFIA 2, which we have been observing in 2016 or 2017. So with another mode instrument, so we have been using narrow bands in the far infrared, in the near infrared, and also we have had some simple observation in the red band. So this is all the data point you're seeing on this graph. So this includes both the broadband in H and K we had previously, and also the new polarization observation on the narrow bands with both IRDIS and simple. But then I've been testing the polarization in very different, well, in different places in the central region. So you can see the big red square is about 1 arcsecond wide in the central region of 1068. So that's the same image I've been showing before. And then I tried to extract polarization on 2 small regions. So the orange region, which is exactly at the center of the AGN, and the green region, which is a little bit off-centered. So we are avoiding the very bright central source, but we're still within the range of the constant polarization orientation. So I haven't shown the polarization angle in the graph, but it's remarkably constant with some variation depending on the well, signal to noise ratio basically. But you can see here the variation of the polarization depending on the wavelength and on the aperture. So the red, as expected, the red aperture is just like slightly increasing with wavelength. With that's actually not new, because there's well, this AGN has been studied a lot over the past 20-30 years in polarization. And so this is already known feature that excuse me, polarization degree is increasing between the visible and the near infrared. But now, if we separate this very central region and the bit of the outer region, we can see the polarization is evolving rather differently. So in the very central region, we have quite large increase, a bit bigger increase than the entire central region at first, up to 150, well, sorry, 1500 microns, nanometers, well, 1.5 microns. And then it decreased a little bit, not very strong decrease, but it goes from, well, 6 to 7% down to 4 to 6%. While actually the green part is mostly, well, not exactly constant, but it's pretty low, and it's way below the value we are measuring for the entire central region, and it then get an increase at the very end. So actually, what we would see in the 1 second aperture is a combination of these two mechanisms and these two different regions that would sort of average the polarization we are measuring from these different regions. So we would have kind of an average polarization degree. But actually, there's probably like 2 different mechanisms at work in these 2 different regions. So in the very central part, we would actually have the light coming from the center, which cross through part of the AGN. So that would absorb, well, that actually would be dichroic absorption. So we would have a specific orientation of the polarization because of dichroic absorption. So that would explain the very high polarization degree in the center. If you remember on the previous map, I'll try to catch that. Yeah, on this map, on the left side, there's a very high polarization degree at the very center, and then it decreased quite rapidly to have very low polarization degree close to the very center. So the very bright spot would actually come from dichroic absorption, so light directly coming from the center, crossing through the material, which will be, well, optically thick, but not that optically thick, so there are still like some photons escaping the medium. And on the outer part, we would actually see this double scattering feature with very low polarization degree, but still the same constant polarization angle. So the problem with these two mechanisms is actually they are ending having the same orientation of the polarization at the end. So they are both expecting to, in this particular geometry, to produce the same orientation of the polarization. So the difference would be only on the polarization angle. So the very high polarization degree would actually come from dichroism, and so dichroic absorption, while the low polarization region would come from double or even possible multiple scattering. So in order to try that assumption, I just changed a little bit the modeling I was doing before. So you can see the two blue curves on the graph are coming from the simulation. So this is done with way smaller optical depths than I was working on before. So we're not in the 150 in V, but that's between 25 and basically 50 for optical depth, which is a bit more reasonable and actually closer to the expected values. And so with the model, we can actually see a very clear increase of the polarization, well, around 1 micron, and then a slower decrease up to 2 or 3 microns. And that will actually come because for example, in the visible, we would not, well, the optical depth is changing a lot with wavelengths, and in the red, for example, we would have very high optical depth, so not a lot of light is actually able to escape from the center, and that's actually what we observe in the simple images where we can barely see the polarization, which is pretty low, so between basically 1 and 2%. And then with increasing wavelength, the optical depth of the medium decreases. And one of the two orientation of the polarization, the one which is favored by the orientation of the grain, start to be able to propagate through the medium. So we would have a very high polarization. And then the second orientation of the light is starting to propagate through the medium because of the lower optical depth. That will actually lower a little bit the polarization degree, because when we will receive both the orientation, that will actually be more close to a classical unpolarized light. So we have brighter flux, but with lower polarization degree. So that's actually worked pretty well with when we're comparing the blue curves to the orange one, which is what we were aiming to explain. And I've also been checking that with this optical depth, the previous model I've been presenting are still able to reproduce this double scattering region on the outer part. So we would be mostly in the second case, so the one on the upper right. So you can see there's a black spot in the very center, which is actually light directly coming from the center. So in this part, it's not polarized because it's just propagating through the medium. But if we put some dichroism on this flux, this would actually orientate and polarize this part, and we would actually see what we observe in AGC 1068. So that is the most recent work I've been doing on AGC 1068. So we would actually be seeing a multiple scattering mechanism at place in the same object, depending on the wavelength and the location around the center of the region. So I guess that shows that how complex these regions can be, and how interesting it is to disentangle these different polarization mechanism in this region, and also the fact that if you took well, a step further in the resolution on the spatial resolution on any polarization maps, you will actually see a lot of different features. Because a little bit like classical imaging, when you're getting to high resolution, you can actually disentangle between two different regions, which were at first stuck at only one resolution unit. So it actually shows how important it can be for both classical imaging and polarization to have access to higher resolution on the object we're interested in. So now I've been shifting to the far infrared, to the work I've been doing over the past year. So, well, I just put back the same picture with the three different mechanisms. And if we're looking in the far infrared, things are getting a bit simpler because we are mostly going to look at emission. Scattering is not very efficient at this wavelengths, and absorption is just, well, pretty much impossible at this wavelength. So we would like mostly see only dichroic emission by allocating grains, which is making things a bit easier. But in order to detect that, we need the elongated grains to be pretty much all aligned, because if all the grains are well randomly orientated, you're not going to have a specific dominant polarization orientation at the end. And one very good way of orientating the grains, actually not the only, but in AGN that's most likely one, is through magnetic field. So if you have a magnetic field and you have a lot of elongated grains on your medium, they are more likely going to align with the magnetic field. And then if you have all these grains at the given temperatures which are going to emit light, they're all going to emit with a preferential direction of the polarization. So this is a short diagram to illustrate that, but you can see that the polarization in the end is pretty much 90 degrees orientated as compared to the orientation of the magnetic field. So because we are mostly tracing magnetic field at each time in the far infrared, that's the reason why we're actually rotating the polarization vector by 90 degrees in order to trace directly the magnetic field and not to have like this different it's not a really assumption, but this very complex map, which are not looking very friendly. While if we just rotate them by 90 degrees, the vector is just going to follow the expected magnetic field around this region. So in order to observe that, I use SOFIA, so the experiment I'm working on, which is also the NASA Stratospheric Observatory for Infrared Astronomy. So this is allowing the fact that the telescope is aboard a plane. That means that we can actually go to the well, higher layer of the atmosphere and get rid of some of the absorption band. And so that allows to observe between 1 microns and 500 microns. So this is like the different instrument on the right hand side. With well, a lot of different features and a lot of different resolving power and a lot of different wavelength coverage. But the one instrument I'm really interested in is actually OC+, so the one in the like bottom right corner in green over there, which is not very well. That's an imager, so it doesn't have a huge of a resolving power, but it has polarimetric capabilities, which is what very interesting to me. And so this is a picture of OC+ on the left side. So that's a picture when it's actually installed within the plane. And so it allows to have polarimetric images between 53 microns and 214 microns with polarization. So here are, for example, one of the maps. So I've been working with Enrique Lopez Rodriguez on the project. And so we have been observing NGC 1068 before. So that's a smooth transition between my first work on 1068 in the infrared and the next AGN I'm going to work on. All the vectors you're actually seeing there are, well, you can also see pretty much the rotating around the center region, but this is rotated by 90 degrees. So this would actually trace the magnetic field along the central region of NGC 1068. So you cannot see actually that here, but it mostly follow the beginning of the spiral arms on the AGN. Yes, so this is for NGC 1068. And since I've been arriving at SOFIA, I've been working on another AGN, which is Circinus, which is here. So it's another bright AGN, a little bit less bright than NGC 1068, but is also a bit closer because it's only 4 megaparsecs away. So you can actually see the same. So the OC+ map on the upper panel, and you can actually see this sort of elliptical orientation of the vectors around the center, which actually following the exact orientation of the rotation of the nucleus. So you can see the CO map on the bottom part, which show the overall rotation of the nucleus in the central region. And we have like the magnetic field orientated, the polarization vector tracing the magnetic field orientating along this specific orientation, which is pretty much expected, but still we have pretty clear pattern of vectors. And so this is very different resolution because we don't have the same angular resolution with SOFIA that we have with SPHERE, for example. So the red spot is presenting basically the beam of the instrument, which is a bit larger. So I think that's about 5 arcseconds for this this specific band. So it's a bit less. Well, we cannot resolve the very inner region with all these different mechanisms I was talking a bit before, but we can now trace the evolution of the while tracing the magnetic field depending on the wavelengths at a bit larger scale. So we are looking at the anterior nucleus region, for example, and the beginning of the spiral arms and spiral disk of the galaxy. So this is the 3 UP+ maps we have been having. So the left part at 53 microns, central part at 89 microns, and the left part, the right part at 214 microns. You can see a quite different evolution of the well, first intensity, so the total flux, which is shown on the upper part, then the polarization flux, which is on the bottom part, and the polarization vectors, which are also changing. Well, of course, you have an effect of the resolution, which is changing a little bit with between all these different bands. But you can see like these trends of pretty low polarization at the very center of the object, and then when we go further, a bit of an envelope of vectors with a bit higher polarization degree. And so this is actually compatible with different models of magnetic field, but I've been trying to fit one of the models to explain that, and that would actually just be magnetic field with well, inclined along the plane of the sky, which would, due to projection effect, reduce the polarization we are seeing from the very center. So here we are. Well, just to finish on these maps, we are. So this is a maps about 100 to 1000 parsec, because we are having pretty much 1 arcsecond for 20 parsec. So this is a bit larger than the scale I was showing before, which were pretty much the entire image was 200 parsec. And the time on target is not that long, because on the left image it's like only 6 minutes on target and 13 minutes on the right side, and we spend a bit more time on the 89 microns map, so it's about 1 hour of observation. So we were able to actually get a very clear signal with this not so long observation, which is pretty nice. And so then we have been able to fit a model. So I'm going to be a bit fast on that. It's still a work in progress, so it is not even the last fit I've been doing. Things have been well improving a little bit since then, but pretty much the idea was to get the azimuthal variation of the magnetic field orientation, and then trying to fit a model with magnetic field, well, expected magnetic field on the plane of the galaxy. And you can see the fit is actually reasonably working well. And we have access to a bunch of parameters. I'm not going to discuss that much, but because they are changing a little bit, and we are mostly constraining. So we have a bunch of parameters which are not well constrained, and some other which are well a bit more constrained, but they are more like so the orientation, like the inclination of the galaxy along the plane of the sky, and the orientation of this nucleus. So the one thing I'm currently trying to investigate on is actually the pitch angle, so the radial variation of the azimuthal angle of the magnetic field, but it's unclear if we can really detect well, variation from 0 from this parameter. So that's the goal for the next couple of months, I would say. So now I'm going to move on to finish, if I still have time for that, by the well, radiative simulation code I've been using and developing actually in Lysia over the past 5 years. So this is just a very yeah.
Because sorry to interrupt, maybe if you can try to finish in like 5 minutes,
Yep.
so we have time for.
Yeah,
thank you.
That's perfect. So this is just a rapid summary of the basic idea of the simulation. So the idea was to get this radiative transfer code to simulate the AGN environment, and so we wanted some 3D grid sampling dust densities to be able to specify exactly which location we want the dust to be located, and to have also a choice in the in the dust population. So we can choose between silicates, graphites, but also more critically for us, pH and electrons in the very central part of the AGNs. So it's because of the mechanism that are included, it's mostly working between the visible and the infrared. It can technically work in outer of this range, but it's not going to be guaranteed because we would need to include more effect to represent decently the physics reality. So there have been a lot of work, not only by me on this code, in order to make it a bit more friendly, in order to have more display. So, for example, this is a work by Tong Lam. Well, you can actually, because you know him, I can just say Lam. So we have been working on the specifically on using the code for the stellar clusters, so which are still unsure, well, within the dust cocoon. So you can actually study the how bright these stellar clusters are depending on their age, because the amount of dust surrounding them is not the same. And so you can see actually a visualization tool in 3 dimensions that Lam have been working on. I've also done some very short tests with Trisha on the stellar environment. So this is just first test. We actually need to go a bit further into that to analyze and see if it's actually working as expected. But the first draft seems to follow pretty much the trends we are expecting from that. So I'm going to go a bit faster on explaining how the code is actually working. So I'm working with photon packets. So we're not using just one single photons propagating through the medium, but actually a bunch of photons, which is allowing to be a bit more efficient in calculation. So yeah, so it's just a grid we are using, but well, that's we can come back on that if you have a question on that. So that allows to have like the dust densities. And you can change between the different species. But more interestingly, yeah, so if you use one photon, it gets absorbed or not, or it gets scattered, but then it's pretty inefficient in terms of you have to do that a huge amount of time to have a decent signal in the end. So the solution, and well, I've not been inventing that, it was actually like already one of the things that was already usually achieved in a radiative transfer code is using photon packets instead of just one single photons. So you can actually either scatter the entire packets or emit the entire packets, or you can have part of the photons which is absorbed and another part which is re-emitted by the population of the dust. So you can actually change because of that the wavelengths, because for example, if you have your photon packet which is absorbed by the dust in the part, you would have you can actually re-emit a bigger number of photons at longer wavelengths. So this is done to keep the energetic balance at equilibrium. So you can see, for example, if you have like your photon packets at the beginning, and you can if they are absorbed and re-emitted, you're going to have a bunch of photons at different wavelengths, but you are going to have more of them in order to keep the energetic balance up. And if you have a scattering event, you can actually because you're not going to have all the photons to scatter in real life, you can actually just scatter a part of your photon packets, and then to keep the other as they were absorbed, in order to have a bit of a easier time to compute all these different mechanisms happening on the different surfaces. So why do we want to keep the energetic balance at equilibrium? Is actually because we can actually also compute the temperature of the cells depending on the dust population we are putting there. So this is a work that has been done by Brockman and Wood a long time ago, like 20 years ago. And so we are basically using the same algorithm to compute the temperature in the cell, so that actually change the temperature of the photons that are re-emitted by this region, because they are going to emit at shorter wavelength if they are higher temperature. So this allows to have pretty complete simulation with including the effect of the ray emission depending on the temperature of the medium. So if you're close to the bright object, it's probably going to be a bit higher temperature than if you're farther away. So that's well, basically the principle of how the code works. And then, well, I'm not going to enter too much into the detail of the phase function, but for each scattering event, we actually compute the exact probability density orientation of the angle, scattering angle after the interaction. So that depends on a lot of parameters. So basically the ratio between the wavelengths and the size of the grains, and you can see like the classical Rayleigh function on the right left side, and then you get some more complex well, phase function depending on this ratio between the wavelengths and the size of the grains. So, well, to finish, you actually have a lot of different, well, what modeling is actually allowing you is to have a bit more information than you can have with observation, because you can actually track the number of scattering events that are undergone by the photons on the way out. You can track the temperature of the medium, which is, well, a bit more complex to do in real life astrophysics. You need some assumption and some computation to reach these maps. You can extract spectra and now even 3D images thanks to LAM. And yes, you can get access to density maps. And so here is an example of a spectra. I think that's one of the initial spectra. And now LAM have been doing like way better spectra after that. And yeah, not to mention, Pierre has also been working on the interferometric part. I don't know if that's still, well, I mean, I know it's usable, but I don't know if that's easy to use yet. But yeah, that's the state of the art. I'm still working on the publishing of the code, because I need to get for the license part of the thing, but it should not take too long now. I've been seeing that over the past months, but yeah, I just need a bit of time to finish the thing and making it properly available to anyone. Actually, it's already available for the observatory people. And so to conclude, I still have a lot of ongoing work. So for example, on the Circinus SOFIA data, I'm still working on the analysis of the data. On the simulation point of view, I'm still also working on the end of the first release of the MontAGN code. And I'm also working on the magnetic field fit to have a model of magnetic field. And in the end, I would be interested to extend this work to have like MHD simulation to have a complete view of the magnetic field in the central region of the AGNs. I've been also presenting basically two AGNs, so NGC 1068 and Circinus, but this is actually part of a large observing program by Enrique I'm working with, and we have a bunch of AGNs. I think we have like now 10 or 12 of them. So we're going to move on to other AGN later on. And also with the incoming instrument with like specifically gravity, which is already on sky, the JWST, which is hopefully going to be launched soon, and ELTs that are going on. There are some major improvements for extragalactic observation, which are expected. Unfortunately, not a lot of that with polarization features, but nonetheless, the gain in resolution is going to be probably critical for extragalactic science. And I'm going to stop there. Thanks a lot for listening. If you have any question, I'll be happy to take them.
Thank you, Luca. Thank you very much.